In plutonium, the alkali metals, groups 1 and groups 2, the alkali metals and the alkaline earth metals, raw materials and raw materials utilization, explosive elements, and the manufacture and commercialization and privatization of explosive elements as registered in the Kenyan explosive materials, explosive works, explosive materials registered in the Oxford University syllabus for the Commonwealth syllabus. Metals which are in the metal processing and manufacture and information processing, which is regulated by the United Nations Organization of the Commonwealth. So group 1, we are dealing with the alkali earth metals, namely silicon, aluminium, and zinc, and other similar elements, and sodium and potassium and nitrogenous compounds that are normally manufactured in the Kenyan industry. And the materials are obtained from natural resources like the Lake Magadi natural salt reserve. It is protected. It belongs to the Tsavo Park. It is a protected area where nobody is allowed to go to unless one has special permission, and unless one knows what one is doing there, and one is not allowed to pick there or anything from there without permission of the Kenyan government or the United Nations Organization, because it is actually a military science, like the military sciences, like the chemistry in contact by G.C. Hill and J.S. Holman from the Oxford University Press. Actually, military sciences, Kenya military sciences, and Oxford University Press military sciences, and the Royal military sciences conditions are fulfilled in this case. That's why I feel free to read such a book, which is actually military secrets in such a closed space with my telecommunication and mastery devices within a closed room where nobody else is allowed to speak to me or to approach the door or to listen to what I'm saying. That means that I'm speaking in a normal whisper tone or in a normal conversational tone. I'm conversational, I am relaxed. And I'm going to speak about the groups 1 and 2, the alkaline metals and the alkaline earth metals, chapter 14 of J.C. Hill and J.S. Holman and G.C. Hill of the Oxford University Press. And this is a dictation exam. This is a comprehension exam. If I comprehend what I do, and what I diligently do, and what I produce and manufacture and register as my work. 14.1 Introduction. The alkali earth metals and the alkaline earth metals are members of the groups 1 and 2 respectively in the periodic table 14.1. Whilst you are studying these elements, look at the following important features. The similarities between the elements in group 1, the similarities between the elements in group 2, the difference between the elements in group 1 and those in group 2, the graduate trends and properties of the elements in the compounds in groups 1 and the similar trends in group 2. Table 1, the members of group 1 and group 2 in the periodic table. Group 1, lithium, sodium, potassium, rubidium, and caesium. Group 2, barium, magnesium, calcium, strontium, and barium. Those are the alkaline earth metals, and the alkali earth metals are group 1, lithium, sodium, potassium, rubidium, and caesium. And the group 2 elements are barium, magnesium, calcium, strontium, barium, and barium. Those are the alkaline earth metals, the 2 groups. There are actually 5 each. In all these metals, the only electrons in the outermost shells occupy an s orbital, hence these elements are sometimes called the s-block elements. Write the electronic structure of sodium and potassium in terms of SPD. Potassium, the electronic structure of lithium is 1s squared 2s minus 2s1. And the electronic structure of barium, magnesium, and calcium in terms of SPD F potassium. You will now realize that all group 1 elements metals have one outermost s electron, whereas group 2 metals have 2 outermost s electrons. These electrons situated much further from the nucleus than all other electrons in a metal are only weakly held by the positive nucleus. Consequently, the atoms of groups 1 metals already lose their single outermost s electrons to form stable with a noble gas electron structure. Stable ions with a noble gas electron structure carrying one positive charge, e.g. Sodium into sodium sodium is reduced to sodium and sodium ions and one electron. Similarly, the atoms of group 2 metals readily lose 2 electrons to form stable ions, which have a noble gas structure carrying 2 positive charges, e.g. calcium is reduced to calcium 2 ions and 2 electrons. Oxidation numbers and ice block elements, tables 14.2 summarize various physical properties of the elements in group 1 and the respective physical properties of the elements in group 1. The physical properties are electron structure, first ionization energy in kilojoules per mole, second ionization energy in kilojoules per mole, and atomic radius nanometers, metallic radius, melting point in degrees Celsius, boiling points in degrees Celsius, degrees centigrade, melting point in degrees centigrade, boiling point in degrees centigrade, density in grams per centimeter, solid electrode potential M plus aqueous over M solid over volts. Look closely at the first and second ionization energies for group 1 elements. The first ionization energy is much lower than the second. In the case of the sodium, it is 9 times easier to remove the first electron than the second. The first electron in an s orbital can be removed from the element easily, but the second electron must be removed from a vulnerable gas core, which is closer to the nucleus, and therefore requires much more energy. Thus, sodium readily forms sodium ions, but never forms sodium 2 plus ions. This means that sodium and other elements in group 1 have only the one oxidation state of 1 plus 1 in their compounds. Look closely at the first, second, and third ionization energies of group 2 elements in table 14.3. Physical properties of the elements in group 2. The elements and the physical properties are beryllium, magnesium, calcium, strontium, and barium. Those of group 1 were lithium, sodium, potassium, rubidium, and calcium, and their electron structures are their physical properties are electron structure, first ionization energy in kilojoules per mole, second ionization energy in kilojoules per mole, third ionization energy in kilojoules per mole, atomic radius per nanometer, and there's a metallic radius, and the melting point in degrees Celsius and the boiling point in degrees Celsius, and the density in grams per centimeter. This is the standard electron potential M2 plus aqueous to M solid over volts. What is the ratio of the first ionization energy to the second ionization energy into the third ionization energy of magnesium? The ratio is decreasing states of stability, decreasing states of stability, and increasing states of reactivity. That means that they are the elements in the outer energy shells are ready to lose the outermost electrons, and not the outermost electrons in the outermost electron shells, and not as ready to lose their electrons in the innermost electron shells, or in the middle electron shells are more ready to lose the electrons, but are less stable than the innermost energy shells. Why is there a greater increase from the second to the third ionization energy than from the first to the second? There is why is there a greater increase from the second to the third ionization energy than from the second to the first? It means that the ions in the second to the third ionization energy need a lot of energy to be released from the third and from the second, but from the first it is impossible, because they are actually bonded to they're in the molecule itself, because they lose this ionization energies. They don't lose the ionization energies because that's not how to explain it. What is the most stable set of group 2 elements? The most stable set of group 2 elements is the smallest state, the smallest ionic radius. The atomic radii of alkali metals are included in table 14.2, and those of alkaline earth metals are included in table 14.3. As one might expect, the atomic radii increases an atomic number down to the groups, since each succeeding element has electrons in one more shell than the previous element. The outermost s electrons in these metals are held very weakly by the nucleus. Thus, the outer electrons can drift from the nucleus than in most of other elements. The outermost s electrons in these metals are held very weakly by the nucleus. Thus, the outer electrons can drift further from the nucleus than in most other atoms, and the elements in group 1 and 2 have larger atomic radii than those elements which follow them in the respective periods. The larger atomic size results in weaker forces between the neighboring atoms since there is a reduced attraction of the nuclear charge for the shared mobile outer electrons as these electrons get further away. Consequently, the metals in group 1 and 2 have lower melting points and lower boiling points than we would normally associate with these metals. Apart from beryllium, all these metal points are less than 840 degrees and all other group 1 elements melt below 200 degrees. In contrast, most of the transition elements melt at temperatures above 1000 degrees Celsius or degrees centigrade. The reduced interatomic forces in the metals makes them relatively soft. All the group 1 metals can be cut with a penknife, and although in the group 2 metals are harder than those in group 1, they are generally softer than transition elements. As we have seen, S-block elements have larger atomic radii than transition. As we have seen, S-block elements have larger atomic radii than transition metals of comparatively the same relative atomic mass. Thus, the S-block elements will be less dense and have larger molar masses. Of the 10 elements in tables 14.2 and 14.3, only barium is more dense than aluminium, a metal normally associated with low density. These densities vary from approximately 1 gram per centimeter cubed to 3.5 grams per centimeter cubed for barium. Most transition metals have a density greater than 7 grams per centimeter cubed. Chemical properties. All these metals in groups 1 and 2 are high in activity electrochemical series. Standard electrode potential tables 14.2 and 14.3 for the conversion of Richmond trace ions is positive and greater than 2.0 volts for all metals except beryllium. Yes, these metals are very good reducing agents. They all react vigorously with water, reducing it to hydrogen. M solid into M plus aqueous plus electron minus, and H2O liquid to M plus an electron is oxidate to a hydride and hydroxide aqueous. Excluding lithium, which reacts slower than all other elements of group 1, the reactivity of the elements with water slowly closely follows the values of E. In group 1, for example, sodium reacts vigorously, fusing and skating. In group 1, for example, sodium reacts vigorously, fusing and skating about on the water surface. Potassium reacts even more vigorously, creating small cracks and pops as the hydrogen explodes and producing a lilac flame as the hydrogen burns. Rubidium and calcium explode violently in contact with water. Do energy values relate to reaction rates or to equilibrium? Do they indicate how fast a reaction will go, or how simply the direction which it should go? Why do you think lithium reacts more vigorously with water than other group 1 elements, even though it has the largest energy? Do energy values relate to reaction rates or to equilibrium? Do they indicate how fast a reaction will go, or simply the direction it should go? The energy changes relates to reaction rates in the sense that the bigger the energy value, the slower the reaction, the slower the reaction to the end product, and to the equilibrium. It will mean that depending on the amount of substrates available for the chemical reaction, the chemicals that will be formed out of all the available reaction of reactant A and reactant B, and if there is a surplus of reactant A, it will be a product C with a surplus A. If there is a surplus of reactant B, it will be a product C and a surplus of reactant B. If it was a surplus of reactant B, it will be a product C and reactant B, and if it is less of reactant A, it will be a product of a product C with less A in it. That will mean that a surplus of reactant B, and if it was less B, it will mean that a product will be made of C and rest products of reactant B, of reactant A. Why do you think lithium reacts more slowly than other group 1 elements, even though it has the largest energy level? Perhaps because it has higher energy shells. When it has higher energy shells, it means that it reacts with electrons and at a lower energy level and with a lower electromagnetic powers, so that it reacts at a lower energy and would react faster if it had lower energy shells. If it had lower energy, if it was closer to the atom, it was closer to the protons and the neutrons. Although electron potentials relate only to aqueous solutions, they also provide a guide to the general reactivity of a substance. All the s-block elements are such good reducing agents that they can react with chlorine, bromine, sulfur, hydrogen, and oxygen on heating. They all of course, tarnish rapidly in air, forming a layer of oxide. In the reactivity of group 1 metals, such as lithium, sodium, and potassium, are usually stored under oil. Thermal stability of salts 14.5. Thermal stabilities of salts. The stability of the salt M plus X minus S solid is dependent on both the size of the ions and the charge of these ions. The greater the charge, the stronger will be the attraction between the ions, and the most stable will be M plus X minus S. The smaller the ions become, the closer they can approach each other in the solid crystal, and the most stable is M plus X minus S as a solid. Thus, we might proceed M plus X minus to become more stable as the ionic charge increases or as the ionic radius decreases. There is, however, one other very important factor to bear in mind during any discussion of thermal stability. When large anions such as carbonates decompose on heating to form smaller ions such as oxides, the crystal containing the latter will generally be more stable than the carbonate, since the charge density on a small oxygen ion will be greater than that on a larger carbonate ion, because the oxygen is O2 and the carbonate is a trioxide ion, and the former will be much more strongly attracted to the cations in the crystal. Furthermore, the smaller O2 ions can get closer to the cations than the larger CO3 2 minus ions. This point has considerable importance in considering the thermal stability of the nitrates, the carbonates, and the hydroxides of the s-block elements. Nitrates V, group 1 nitrates V, except lithium nitrogen trioxide, decompose on heating in the Bunsen flame to form their corresponding nitrates 3 nitrates, which are stable. Sodium nitrate solid can be decomposed to sodium nitrogen dioxide solid and a half oxygen molecule in gas form. However, group 2 nitrates V and lithium nitrogen trioxide decompose on heating to form their corresponding oxide. Magnesium nitrogen trioxide to solid plus magnesium oxygen solid. Magnesium nitrogen trioxide solid is reduced to magnesium oxygen solid and nitrogen oxygen gas and a half oxygen gas molecule, and 2 lithium nitrogen trioxide are reduced to lithium dilithium oxygen solid and 2 nitrogen dioxide gas and a half oxygen gas molecules. This suggests that the decrease in size from nitrogen trioxide to nitrogen dioxide stabilizes the group 1 nitrates to heat, but that the group 2 nitrates we can only achieve thermal stability by decomposing from the nitrate to form the much smaller oxide ion carbonates. The pattern of thermal stability amongst the carbonates is very similar to that of the nitrates. The carbonates of group 1 except lithium 2 carbonates are stable at the temperatures of the Bunsen flame, but those of group 2 decompose at this temperature to form the corresponding oxide. Magnesium trioxide is reduced to magnesium dioxide S and carbon dioxide G. Here again, the group 2 compounds are achieving thermal stability by forming their oxide. How do you think the thermal stability of magnesium dioxide will compare with that of barium carbonate? How do you think the thermal stability of magnesium carbonate will compare with that of barium carbonate? Explain your answer. Magnesium carbonate is more reactive than barium carbonate and therefore will react more exothermically to form a more stable compound, a more thermally stable compound, because of its reactivity for the cations. Hydroxides, yet again, the pattern is repeated. The hydroxides of group 1 are stable, but those of group 2 decompose on heating magnesium hydroxide S into magnesium dioxide S plus H2O. The solubility of salt stable 14.4. Table 14.6, the solubility of salts. The table 14.4 shows the results obtained when 0.1 m solutions of magnesium ions, calcium ions, strontium ions, and barium ions are treated with various molar solutions. Notice that the sulfates, 6, and carbonates, ethanoids, oxalates, and chromates, 6, and group 2 metals become more insoluble as atomic number increases, whereas the hydroxides become more soluble. These results are confirmed by the values of solubilities quoted for the sulfate 6, carbonates, chromate 6, and nitrous 5, and hydroxides 14.5. When an ionic compound dissolves in water, the following process occurs. N plus X minus S plus aqueous is reduced to N plus aqueous plus X minus aqueous. We can picture these processes as the result of two stages. First, the separation of ions in the solid, i.e. N plus X minus the solid is reduced to N plus G plus X minus G, which is the reverse of the lattice formation process and requires the input of the lattice energy followed by the hydration of the separated ions by water, i.e. N plus gas plus X minus gas plus aqueous is reduced to N plus aqueous plus X minus aqueous. The ionic radius of N plus and X minus increase, the heat change in both of these processes decreases. The reverse lattice energy process becomes less endothermic and the hydration becomes less exothermic. Consequently, a decrease in the endothermic process may be cancelled by a decrease in the exothermic process, and it is therefore difficult to make predictions about changes in solubility from changes in ionic size, section 11.4. Therefore, are however one or more general patterns and trends in the solubility of groups 1 and 2 salts. 1. All common group 1 salts are soluble. 2. Salts of group 2 cations containing anions with charge of -1, e.g. chlorides. Nitrates 5 are generally soluble except for the hydroxides. Look at the solubilities of these various magnesium salts, all of which contain an anion with charge -1 in table 14.6. Approximately how much more soluble are the other compounds in table 14.6 compared to magnesium hydroxide? Calcium hydroxide is more soluble than magnesium hydroxide. Magnesium hydroxide is more soluble than strontium hydroxide. It is more soluble than barium hydroxide. Magnesium hydroxide is more soluble than barium chromate, strontium chromate, calcium chromate, magnesium chromate, barium carbonate, strontium carbonate, calcium carbonate, magnesium carbonate, barium sulfate, strontium sulfate, calcium sulfate, magnesium sulfate are all less soluble than magnesium hydroxide because of the higher energy levels. Magnesium nitrate, calcium nitrate, strontium nitrate, and barium nitrate are less reactive than magnesium hydroxide. The nitrates are less reactive than magnesium hydroxide. And nitrates 5V are less reactive than the magnesium hydroxide. Magnesium nitrate, calcium nitrate, strontium nitrate, and barium nitrate are less reactive than magnesium hydroxide. Why are the solubilities given in moles per 100 grams of water rather than grams per 100 grams of water? They're given in moles because of their molecular weights, which form a more soluble reaction than a more soluble compound than mixtures of the same elements when measured in grams. Salts of group 2 cations contain anions with a charge of -2, e.g. sulfates. 6 carbonates are generally insoluble except for some magnesiums and a few calcium salts. Furthermore, there is a distinct increase in solubility as the atomic number of the metal rises. Thus, beryllium and magnesium sulfates are very soluble in water. Calcium sulfate is sparingly soluble, but strontium and barium sulfates are virtually soluble. The solubilities of some compounds of group 2 metals are shown in table 14.5. Thus, beryllium and magnesium sulfates are very soluble in water. Calcium sulfate is sparingly soluble. but strontium and barium sulfates are virtually insoluble. Why do the sulfates 6 and carbonates, ethanoids, oxalates, and chromates 6 of the alkaline earth metals show similar trends in solubility? The solubility of these earth metals, the solubility of the salts decreases as the atomic number of the metal ions decreases, and this pattern is opposite to that observed for the hydroxides and fluorides. Although it is difficult to relate solubilities accurately to such fundamental properties, as lattice energy and hydration energy, it is possible to make a semi-quantitative analysis in these terms. Lattice energies of the sulfates, 6 of the groups 2 metals, change relatively little from the magnesium sulfate to barium sulfate, since their values are determined largely by the reciprocal of the sum of the ionic radii in brackets 1 over R plus R minus close the brackets. The ionic radius of the sulfate 6 ion R is so large that the changing size of the much smaller cation makes very little difference to 1 over R plus R minus close the brackets. However, the changing size of the cation does cause considerable differences in hydration energy. From magnesium to barium, the increasing size of the cation reaction results in the smaller hydration energies of the decreasing exothermicity of the hydration processes causes a decreasing solubility of the compounds. The solubilities of the carbonates, ethanoids, oxalates, chromates, and nitrates of group 2 metals vary in the same way as those of the sulfates because of the ions in all these compounds are relatively large compared to the constituent cations. However, this trend of decreasing solubility with atomic numbers, a number for the alkaline earth compounds, is reversed in the case of the hydroxides and fluorides. In these compounds, the ions OH and F- are much smaller, and that energies are no longer approximately constant but decrease with increase in cation size. Furthermore, the change in lattice energies is greater than the change in hydration energies, and consequently hydroxide and fluorides become more soluble as the group is resembled occurrence of the s elements. The alkali metals occur in nature only as +1 ions. Sodium and potassium are, of course, the more commonest group 1 metal ions, being 6th and 7th most abundant of all elements in the Earth crust. Figure 14.1. Lithium is found in trace amounts in virtually all rocks and trees, but rubidium and calcium are very rare. Francium, the last element in group 1, does not exist naturally. It has only been obtained in tiny amounts during nuclear reactions, and even those amounts disappear rapidly as the radioactive francium disintegrates and forms more stable compounds. Oxygen 50%, silicon 23%, aluminium 8%, iron 5%, calcium 3.5%, sodium 2.7%, potassium 2.5%, magnesium 2.0%, phosphorus 1.2%, other elements 2.1%. Many of the compounds of alkaline metals are soluble in water. It is not surprising that they are found in relatively large quantities in seawater and as salt deposits, in which they are formed by the evaporation of brine. However, many soluble clays such also contain alkaline metal ions combined as complex silicates and aluminates. The alkaline earth metals occur in nature only as 2+ ions, as these +2 ions react with -2 ions to form insoluble compounds. It is not surprising that group 2 elements exist in nature principally as their carbonates, silicates, and sulfates. The only beryllium mineral found in any quantities is the silicate beryl 3 beryl silicon trioxide and aluminium silicon trioxide 3. Emeralds are in fact crystals of beryl, colored green by traces of chromium. Magnesium is the eighth most abundant element in the Earth's crust. It is found extensively as a carbonate in magnesite, magnesium trioxide in dolomite, magnesium trioxide, calcium magnesium tricarbonate, calcium tricarbonate, as a silicate in minerals such as asbestos, 3 magnesium silicon trioxide, and calcium silicon trioxide, and magnesium silicon magnesium ions in seawater. Calcium is the fifth most abundant element in the Earth's crust and the most abundant S-block element. Vast quantities of calcium occur as a carbonate in chalk, limestone, and marble. Each of these minerals is observed to have been formed by the effect of high temperature and high pressure on the accumulated skeletal remains of marine mammals. Marine animals. Smaller quantities of calcium occur as marine animals. Above left, the white horse carved in the white chalk upton at the Affinton Berkshire. Above left, the white horse carved in the chalk downland at the Affinton Berkshire. Above left, the white horse carved in the chalk downland at Affinton Berkshire. A large crystal of salt. Smaller quantities of calcium occur as sulfates in anhydride calcium sulfate and gypsum calcium sulfate to H2O. These sulfate ores are thought to have resulted from the action of sulfuric acid produced from the oxidation of sulfide minerals on limestone. Sodium and barium are much rarer elements. The commonest of sodium is strontianite, so strontium carbonate, and that of barium is barium sulfate. Left on the Ethiopian basin to carry salvation salt to the shore. Further from Ethiopian rockman at the lake, Asada salt bags shaped slabs of salt into conveniently shaped sized bars. The average abundance of radium, the last element in the group in the Earth's crust, has been estimated of less than 1 part per million. Radium exists naturally as a radioactive element formed during the nuclear disintegration of heavier elements such as uranium. Manufacture of S-block elements. In order to extract the S-block elements from the naturally occurring compounds, it is necessary to reduce their positive ions, i.e. M plus aqueous plus electrons to M solid, or M2 plus aqueous plus 2 electrons to M solid. This reduction can be done either chemically or electrolytically, but the large negative electron potentials of the S-block elements mean that the chemical methods are virtually impossible, since they would require a reducing agent stronger than the alkaline or alkaline earth metals themselves. Consequently, these elements are usually extracted by electrolysis. The electrolytes used are always fused compounds rather than aqueous solution, since water in the solution would be discharged at the cathode and reverse the S-block ion. For example, sodium plus electron is reduced. Sodium energy volt of minus 2.171 volts, and H2O plus in minus into a half hydrogen and OH minus with an energy output of minus 0.42 volts. The more positive, less negative electron potentials for the lower reaction means that it will occur in preference to the one above. Of the elements in groups 1 and 2, sodium and magnesium are in much higher demand than the others. Each of these elements is obtained by electrolytes of its chlorine. Look closely at the figure 14.2, which shows a simplified diagram of the down cell in which sodium is manufactured. Sodium is manufactured in a hole through which sodium chloride is added in a circular steel cathode and a cylindrical graphite anode. Sodium is produced at the cathode, and chlorine is produced at the anode, at the cylindrical graphite anode. The sodium is turned into sodium chloride is turned to molten sodium chloride, which is the electrolyte in the circular steel cathode. The electrolyte contains sodium liquid and chloride liquid ions. At equations on the present which at each electrode during the manufacture of sodium. In the downside, the cathode is made of steel, but the anode is made of graphite. Why is the anode made of graphite? In spite of the fact that steel would be a better conductor, because of the reactions between because of the chemical reactions between steel and chloride into ion chloride, and which is avoidable by exchanging the anode with the steel anode with a graphite anode, because chloride has a higher potential for hydroxide and for the hydrogen in the hydroxide than the carbon. Why is the anode made of graphite? Is part of the fact that steel would be a better conductor because of because of the reactions between steel and chloride. It would corrode, the steel would corrode in time and would dissolve into the liquid, and the reaction would stop because of the reaction of steel and of iron and chloride. The reaction will stop because there will be no anode left for the further reaction. Why is it necessary to incorporate hoods and steel core cylinder in order to prevent the product of the anode from mixing with the product of the cathode? For the same reason, to stop the reaction, to stop the chloride from reacting with the to increase the reaction of sodium with the electrolyte, because sodium is more reactive than steel. Other cathode. It means that there is a more competitive reaction at the cathode than at the anode, and it prevents the anode from corroding faster than the cathode. Since the extraction of these S-block elements must involve fused compounds rather than aqueous solutions, large quantities of energy are required not only for the electrolytic process but also to melt the electrolyte. Why do you think that so many electrolytic manufacturing plants are located near supplies of hydroelectricity? Because of the availability of hydroxide and oxygen and hydroxide ions in the chemical reactions. In the sodium chloride solution. For the reaction processes are the cathodes and the anodes with water, with oxygen and hydroxide ions. And these include as a naturally occurring raw material is usually mixed with some other compound. For example, in the extraction of sodium electrolyte, sodium chloride contains some calcium chloride. How does the addition of calcium chloride reduce the energy expenditure? Calcium is used as a reserve. Is used as the electrolyte as a reserve positive ion when the sodium is extracted from the solution. In view of the calcium chloride added to the electrolyte, what substance will contaminate the sodium produced at the cathode? Most likely iron, because it reacts competitively at the cathode for the negative ions, for the cathode and for the negative ions. Use of the S-block elements and their compounds. In spite of being so reactive, sodium, magnesium, and other S-block elements have many important uses. Probably the most important use of sodium is a liquid coolant in nuclear reactors. Fast nuclear reactors such as that at Dounreay operate at a temperature of about 600 degrees. Water which boils at 100 degrees is therefore unsuitable as a cooling liquid in this case. But sodium, which melts at 998 degrees and boils at 892 degrees, is ideal for this purpose. Furthermore, sodium is a much better thermal conductor than water and almost as mobile as a fluid. It can therefore be circulated easily around the hot reactor core and will transfer the heat away even more effectively than water. Assuming that the sodium can be prevented from coming into contact with air or moisture, the only major problem in its use as a liquid coolant is that it can act as a solvent for various metals which might otherwise be used for the reactor core and the cooling system. Fortunately, iron and other transition metals are virtually insoluble in the liquid so that they can be used in the construction of the reactor core and the cooling pipes. Sodium's high electrical conductivity and low density have led to extensive testing to see whether sodium can be used in electricity cables. Of course, sodium wire could never be used because of its reaction with air and water and its poor mechanical strength. However, a method can be devised to overcome these problems by extruding a tube of polyethylene polyethylene and simultaneously filling it with sodium. Another important use of sodium is an alloy with lead in the manufacture of tetraethylene lead from chloroethane. Lead sodium alloy, lead plus 4 sodium plus 4 carbon to hydrogen 5 chloride to carbon to hydrogen 5 for lead plus 4 sodium chloride tetraethylene lead petroleum. Tetraethylene lead petroleum is used as an essential additive for petrol. Each gallon of petrol contains about 2 centimeters cubed of tetraethylene lead, section 25.6. Sodium is also used in the reduction of titanium for chloride to titanium by the Goldschmidt process and is in the family of yellow sodium vapor street lamps. In the metals industry, sodium cyanide is used in the extraction of gold and in the hardening of steel. Sodium hydroxide is the cheapest industrial alkali. Thousands of tons are used annually in the manufacture of rayon, cellulose, acetate, paper, and soap. Sodium polyphosphate, sodium 6, potassium 6 or 18 is used as a water softener, and sodium nitrate 3 and sodium nitrite is used as a preservative in food. The other metals in group 1 are used much less extensively than sodium in its compounds. Potassium is used to make potassium superoxide, KO2, which reacts with water to give oxygen. 4 potassium oxide, 4 KO2 plus 2 H2O. This gives you 4 KOH plus 3 O2 potassium oxide. Potassium oxide can therefore be used as an emergency source of oxygen in mines and in submarines. Potassium chloride is used as a fertilizer, and potassium nitrate is used as a constituent of gunpowder. Potassium oxide can therefore be used as an emergency source of oxygen in mines and in submarines. Potassium chloride is used as a fertilizer, and potassium nitrate is an essential constituent of gunpowder. Potassium chloride is a fertilizer, and potassium nitrate is an essential constituent of gunpowder. Potassium nitrate is also a fertilizer. Owing to its very low fast ionization energy, calcium is used as a light-sensitive surface in photocells, devices used to convert light signals to electrical signals. Figure 14.3 shows a simplified diagram of a photocell circuit. The evacuated tube contains 2 electrodes, one of which is coated with calcium or an alloy of calcium, antimony, and silver. In the absence of light, the photocell does not conduct electricity. However, when the calcium-coated electrode is struck by light, it emits electrons which are attracted to the positive electrode and an electric current flows in the circuit. However, when the calcium-coated electrode is struck by lightning, it emits electrons which are attracted to the positive electrode and an electric current flows in the circuit. However, when the calcium-coated electrode is struck by light, it emits electrons which are attracted to the positive electrode and an electric current flows in the circuit of energy shells. Television, pickup devices, and photograph for light noise incorporate the use of these photocells, energy shells, photo energy shells. Magnesium is by far the most commonly used metal in Group 2. It is used extensively in the preparation of lightweight alloys with a high tensile strength, and particularly in the construction of aircraft parts and household goods. Although pure magnesium has poor structural strength, this can be increased by alloying it with aluminium, zinc, and manganese. The aluminium increases the tensile strength of the alloy, the zinc improves its machining properties, and the manganese reduces corrosion. The aluminium reduces the tensile strength of the alloy, the zinc improves its machining properties, and manganese reduces corrosion. When manganese burns in air, it emits a bright, intense light. When magnesium burns in air, it emits a bright, intense light. Magnesium, DJ Magman. When magnesium burns in air, it emits a bright, intense light. Because of this, magnesium powders and ribbons are used as light sources in the photography. Flash bulbs contain magnesium or aluminium foil in an atmosphere of oxygen. When the bulb is fired, an electric current passes through the metal, which is heated up and then suddenly flares into reaction with oxygen. When magnesium burns in air, it emits magnesium burns in air, it emits a bright, intense light. Because of these, magnesium powders and ribbons are used as light sources in photography. Flash bulbs contain magnesium or aluminium foil in an atmosphere of oxygen. When the bulb is fired, an electric current passes through the metal, which is heated up and then suddenly flares into reaction with oxygen. The most commonly used compounds of magnesium are magnesium oxide, magnesium hydroxide, and hydrated magnesium sulfate. Magnesium sulfate 7H2O. Magnesium oxide is used as a lining for high-temperature surface furnaces because of its exceptionally high melting point and low reactivity. Magnesium hydroxide is a very weak alkali. Because of this, it is an important constituent of toothpaste. It neutralizes acids that would otherwise cause decay, and suspension of magnesium hydroxide in water, commonly called milk magnesium, is used to treat acid indigestion. Because of this, it is a very important constituent of toothpaste. It neutralizes acids that would otherwise cause decay, and a suspension of magnesium hydroxide in water, commonly called milk magnesium, is used to treat acid indigestion. Magnesium oxide is used as a lining of high-temperature furnaces because of its exceptionally high melting point and low reactivity. Magnesium hydroxide is a weak alkali. Because of this, it is an important constituent of toothpaste. It neutralizes acids that would otherwise cause decay, and a suspension of magnesium hydroxide in water, commonly called milk magnesium, is used to treat acid indigestion. Beryllium is too rare and costly for any large-scale uses, but is used for hardening alloys and other metals such as copper and nickel. Beryllium copper alloys are particularly resistant to seawater corrosion and are therefore used for small marine parts. Calcium, strontium, and barium have very few uses owing to their high reactivity. The affinity of these elements for oxygen results in the use as deoxidizers in steel production and as getters, i.e. removers of traces of oxygen inside electron tubes and radio valves. By far the most commercially important compounds of calcium are lime, calcium oxide, and limestone, calcium trioxide, calcium carbonate. Limestone, of course, is the use of lime. Many thousands of tons of lime are used annually in counteracting soil acidity and the production of calcium hydroxide. The cheapest alkali, enormous quantities of lime are used in the manufacture of plaster, mortar, and cement. The salts of calcium, strontium, and barium produce beautiful flame colors when heated to high temperatures in a Bunsen flame. Calcium salts red, strontium salts crimson, and barium salts pale cream. As a result of these, volatile compounds of these elements are used in the production of colored military signals and in fireworks. Summary: in the alkali and alkaline earth metals, the only electrons in the outermost shell occupy an s orbital. The atoms of these s orbital metals readily use their outermost s electrons to form stable ions. M plus if the elements are in group 1, and 2 plus if the elements are in group 2. The metals in group 1 and group 2 show only one oxidation number in the compounds. +1 for group 1 elements and +2 for group 2 elements. The S-block metals have lower melting points, lower boiling points, lower densities, and they are softer than tertiary metals. The S-block metals are high in the activity series. They will all reduce water to hydrogen, and they alternate rapidly in air, forming a layer of oxide. Volatile compounds of calcium, strata, and barium are also used for military fireworks. The compounds of group 1 metals are thermally more stable than those of group 2 metals. But the carbonates and hydroxides of group 1 metals, except lithium carbonate, do not decompose at 1000 degrees, but those of group 2 metals decompose their oxides on heating. All common group 1 salts are soluble. Salts of group 2 cations containing anions with the charge of -1 are generally soluble except for the hydroxides. Salts of group 2 cations containing anions with the charge of -2 are generally soluble. The S-block elements are manufactured by electrolysis of the molten compounds. Sodium and magnesium are the most widely used S-block elements. Sodium is used as a liquid coolant in nuclear reactors as an alloy with lead in the manufacture of tetraethyl lead for anti-knock in petrol. Magnesium is used extensively in the manufacture of low-density, high-strength alloy.